All right, folks, worksheet number 3, equilibrium, another short worksheet. For the simple reaction of carbon monoxide plus oxygen giving you carbon dioxide, list the type of bonds that must be broken. Well, they're all covalent. And the types of bonds that must form, well, they're also all covalent for the reaction to take place. So let's actually look at what's going on. We have carbon, and it's bonded to oxygen. Right, so we have a bond here. And then we have another carbon bonded to oxygen. All right. Now the concept is this thing has to hit an oxygen molecule, which is oxygen bonded to oxygen. So what do we have to break? We have to break a single bond or double bonds. We have to break these double bonds actually to form CO2, because one of these oxygens can go with that carbon and one of these oxygens can go with that carbon. So what would be a really good orientation for this to happen? Well, for example, we could think of here if we had O2 bonded to itself like this, and then we had a carbon bonded to an oxygen molecule, all right, and it's actually double bonded already. And it comes along and it whacks into this, and then we have another carbon bonded to an oxygen molecule, and it whacks into that one, an oxygen atom, excuse me, and it whacks into that one. Well, then what we can do is we can break this bond here between the oxygen and the oxygen, and we'll end up with carbon doubly bonded to oxygen, doubly bonded to oxygen. Oxygen doubly bonded to carbon, doubly bonded to oxygen. Now, what orientation really works best for this? We have no idea. We can't see it. So all we're doing is theoretically coming up with some ideas that match what we think all of these molecules really look like. Okay. What is equilibrium? Well, equilibrium, we talked a lot about a seesaw, about it being balanced between someone over here and someone over here, right, as defining equilibrium. Another thing that we could think of is if we have an equilibrium reaction, that the reaction is going forward at the same rate that it is going backwards. Right? And the easiest thing for us to do, I think, is to think about a bottle of water, where the bottle of water, the water is always evaporating. So here I have a bottle of water. If I leave the water just sitting open, the water is going to evaporate, and over time all of it is going to evaporate. Think of it as soda, for example. All of the carbon dioxide that's currently in the liquid will eventually come out and the soda will get flat. However, if I have a lid on top of this water and the water is sealed, then this water is going to evaporate. All right, but the problem is that after a little while, the air up here is going to be holding as much water as it can hold. And as a result, some of those water molecules are going to be going back down into the liquid. And what's going to happen over time is the same amount of water that is evaporating is always going to be going in the same direction. So even though water is evaporating, water is condensing at the same rate. That's equilibrium. They have reached a balance. They've reached a state of equilibrium. So what does the double arrow indicate about a chemical reaction? Well, look at what we have right here. That is essentially a double arrow. The water is evaporating as fast as it is condensing. So I think of this in terms of a chemical reaction. Right? I could think of a chemical reaction as, oh, I don't know, C6H12O6 plus O2, 6O2 gives 6CO2 plus 12H2O. Now this reaction can go in both directions, right? And it does go in both directions. The direction in this direction is called respiration. And the one that's going in the opposite direction is called photosynthesis. You should remember this from biology. All right, so we have one reaction going in one direction, one reaction going in the other direction. Now let's say that they are at equilibrium. Well, guys, that's really what we want in our world. We want it to be in equilibrium. But right now we're developing too many greenhouse gases. We are definitely going further to the right in that we are developing more carbon dioxide than we are developing oxygen. Right? But anyway, that's the very simple. Very simply, that's really what it means. It means that the reaction is going in both directions. Now, what does it mean to say that the state of chemical or physical equilibrium is dynamic? Well, the word dynamic means it's always going on, and again, the water, the evaporation of water that we were talking about, where it is evaporating at the same rate that it is condensing if we're in a closed bottle. Right? The water is evaporating at the same rate that it is condensing. That is called dynamic equilibrium because the evaporation is still going on. The condensing is still going on. So it's dynamic in that it's always changing. It's always going on. Okay. Last question, I think. How does a catalyst work? Well, remember what a catalyst is doing is the catalyst is lowering our activation energy to a lower level. All right? So how exactly does that happen? Well, think of it as how does a key work to get into your house? A key lets you in because you have a lock and you put the key in the lock and it opens the door. Well, think about enzymes in your body, in your stomach. That's exactly what's going on. Is there enzymes, and the enzymes kind of look like a key. And they have certain pieces hanging off of them like this that are waiting for certain sugar molecules or whatever to come along, and they hook right into those things, and they're able to rip them apart. They help to rip them apart. So what that does is they help to rip them apart. They make it happen easier, so they lower the activation energy of the reaction. Okay, folks, that's it. If you have questions, please see us in class. We'll be happy to help you. Take care. Bye-bye.